Hey guys, so in the last lecture, we have seen ratio of the tensions of the flat belt drive. That if we take the ratio of the slack side tension and tight side tension, then what we will get. So that we have seen for flat belts. Now today we will see for V belts or rope belts. So that is for V belts or rope belts. So in V belt and rope belt, the belt is not flat but in shape V type. So suppose this is our belt and uh, suppose it is creating an angle that is equal to 2 alpha, and this is the center line of that V belt. Now the tight side and the flat side. So suppose this is our wheel. So suppose this is our wheel. So this is the V belt. So there will be a tight side and the slack side. So suppose this is the slack side, that is T, and this is the tight side, that is T plus delta T. And the friction will be acting in the direction on the slack side, that will be the friction force, that is Fr, I can call it, which is equal to mu into normal. Mu into normal. So what is the normal force here? So the normal force here, in that is in upward direction, will be equal to, what will be the normal force? So to calculate the normal force here, so let's see this diagram. So suppose this is the V belt. So here the normal force will act perpendicular to the surface on both the sides here. So suppose this is the normal force R on both the sides. It is creating an angle that will be equal to alpha on both the sides. So this is the alpha angle. Now, on the vertical side, the R sine alpha force will act. As here there will be R cos alpha, so here it will be R sine alpha. So similarly, here also the R sine alpha force will act. R sine alpha. So to balance this force, according to Newton's law, the normal force that will act here will be, so here the total force acting, sorry, not balance. So the total force acting on upward direction due to this normal, that is R sine alpha and R sine alpha. So that is total 2R sine alpha. So here it is 2R sine alpha here total. So now we will resolve the forces in both the directions. So the I can call T1 as the tight side and T2 as the slack side. So let's balance these forces in all the directions. So first, let's balance the forces normal in the normal directions. Uh, so let's do tangentially. So on the left side and on the right side, let's balance. So on the left side there is a friction force here. So there is friction forces, there is mu into normal. So what is normal? So normal is 2R sine alpha. So I can write here is 2R sine alpha. So that is on the left side, and on the force, that is T. But vertically, so this angle is suppose delta theta by 2. So suppose this angle is delta theta, so this angle will be delta theta by 2, and this angle will be delta theta by 2. So vertically, so there will be T cos delta theta by 2, T cos delta theta by 2. And now on the right hand side, so on the right hand side is equal to, the forces are T plus delta T, that is T plus delta T here. So that is T plus delta T into, similarly here also it will be cos delta theta by 2. So if I open the bracket, so what will happen is that this T, uh, so let's open the bracket and let's see what will happen. So here I just forgot to keep this plus sign here. So here this T cos delta theta by 2 will get cancelled. So on the left we are left with 2 mu R sine alpha is equal to delta theta cos delta theta by 2. So now as uh, cos as theta delta theta is very very small, so when theta is very very small then cos theta is equal to 1. So we can consider this cos delta theta by 2 as is equal to 1. So here, so we are left with that uh, so sorry here, just the normal force which we are taking is just r, so there will be no sine alpha, so it will be just 2r, so no sine alpha here, so it will be 2 just 2 mu r. So here we are left with here 2 mu r is equal to 2 mu r is equal to delta t. Now we have resolved the forces uh, horizontally. Now we have to resolve the forces vertically. So vertically we have 2r sine alpha here. That is 2r sine alpha, and in on the bottom side, so this force will be normal will be sine alpha, that is t sine delta theta by 2. So that will be t sine delta theta by 2 plus here it will be t plus delta t into sine delta theta by 2. So this force, so this t plus delta t, this t plus delta t, and this angle is delta theta by 2. So this in this direction, so it will be t plus delta t sin theta by 2. So if we resolve these forces, so what we will get is 2r sine alpha is equal to uh, 2 times, so there is t sin delta t theta by 2, so here also t into multiplied with this, so it will be 2 times sine theta t theta by 2 plus delta t sine theta by 2. Now as theta by 2 is very very small, so we can write sine theta, when sine theta is very very small, we can write sine theta is equal to theta. So this term delta, so it will be, so we can remove here this sine, so we are left with sine delta t into sine into delta theta by 2. So this is at 2 times delta, so it is, this small is also small, so these are very very small terms, so we can neglect this whole term. So after neglecting, we are left with 2r sine alpha is equal to 2t sine delta theta by 2. So 2 gets cancelled. So we are left with r is equal to here. So we can write here sine theta is equal to theta. So sine we can remove. So we can write here t delta theta by 2 divided by sine alpha. So t delta theta divided by 2 sine alpha. Now this one term, and uh, in above you found one term, so this, so let's compare this both the terms. So here r is delta theta, so what is the here r, so it is delta t by 2 mu. So let's compare this both the term. So what we'll get is here, just I will rewrite the term here again. So that is 2 mu r is equal to delta t. This 2 mu r is equal to delta t. So let's supply this r here and let's find delta t. So why we are making delta t a subject? Because our goal is to find here ratio of the tension, there is T1 by T2. So T1 by T2 we have to find. So therefore we are making delta t as a subject. So here if I supply this, so I'll get 2 mu into T delta t delta theta divided by 2 sine alpha is equal to delta t. So 2 gets cancelled. So let's bring t on the right hand side. So I'll get mu delta theta by sine alpha is equal to delta t by t. So that is mu theta by sine alpha. Now if I integrate on both the sides, so here from t1 to t2, so that is tight side to slack side, So and here 0 to theta. So what we'll get here is that as it is delta 1 upon t delta t, so here we will get is that is ln ln t, but is t1 t2, so ln, so it will be ln t2 by t1 here. So here it will be, sorry, here we are taking from t2 to t1, that is from tight to slack. So here we are taking from t2 to t1. So here it will be ln t1 by t2. So it will be ln t1 by t2. So this will be ln t1 minus ln t2. This will be ln t1 by t2. And here the integration will be mu upon sine alpha is constant, and the integration of delta theta will be theta, and theta minus 0 will be theta. So if I bring ln on the right hand side, so I'll get t1 by t2 is equal to e raised to mu theta divided by sine alpha. So in the flat belt, our formula was T1 by T2 is equal to e raised to mu theta. But on the for the this V belt, we have got an extra term, that is sine alpha. And if you have to bring sine alpha above, you can write cosec alpha also. So this is the simple derivation which you have to remember. This is for the flat, and this is for the V belt. This is for V belt. So this in exam for calculating for exam numericals you have to remember. Now let's see. So now let's see another topic, that is power transmitted by a belt. So power transmitted by a belt, to find the power, what is the formula for power first? So we know that the formula for power is nothing but force into velocity. We can call it as force into velocity. So what is here force? So the force is the difference between the two tensions on the tight side and the slack side. So we can call it as T1 minus T2. And what is the velocity? So velocity is the distance moved per unit time. So that is the velocity. So the power is nothing but T1 minus T2 into V. So this relation gives the power transmitted irrespective of the fact whether the belt is on the point of slipping or not. If this is the relation between T1 minus T2, sorry, T1 and T2 for a belt drive, uh, as we know that for the belt drive, flat belt is given as T1 by T2 is equal to e raised to mu theta. If it is not, no particular relation is available to calculate T1 and T2. So if this relation is not given, so we cannot calculate T1 and T2. So next, if I want to find the maximum power transmitted through the flat filter, that is how much is the maximum power that can be transmitted, maximum load. That is very much important to transmit the power as to avoid the breakage of the belt or slip of the belt. So maximum power, so to find any maximum, we what we do is we just derivate the equation and equate it to 0. So if it is desired that the belt transmit maximum power, so it has to follow two conditions. First, the larger tension must reach the maximum permissible value for the belt, and the belt should be on the point of slipping, that is maximum frictional forces are developed in the belt. So let's take T1 as a common first. So what is our goal? That is T1 should be maximum. That is so let's take T1 as common. So T1, if I take common, so we are left with 1 minus T2 by T1 into V. So if I reciprocate this, reciprocal of this, so it will be 1 minus 1 upon T1 by T2. So as you know that T1 by T2 is nothing but e raised to mu theta. So I can write here P1 P is equal to T1, not P1 only, P is equal to 1 upon 1 upon e raised to mu theta into V. Now what we know that this all terms are constant. So let's take this whole term as a constant, as a k small. So T1 kV. So now what is T1? So T1 is the tension. It is on the tight side. So the T, what is the total tension T? So T will be equal to T1 plus TC. Now here, what is TC? So here TC is nothing but centrifugal tension. So here the maximum tension T in the belt should not exceed the permissible value, and hence treating T as a constant and differentiating the power with respect to velocity V, equating the sum equal to 0. So now let's just differentiate this d power with respect to velocity v, and considering this as a constant. So what we get is dp by dv is what we are interested in finding. So dp by dv is equal to, here it is t1. So let's uh, instead of sorry, so here instead of t we are putting t1 plus tc. So how we'll find? So t1 we have to replace here. So if I make t1 as a subject, so we are left with t minus tc. So here instead of t1, what will be, will be t minus tc into kv. So here if I so our formula for power is t kv minus tc kv. So here now if I differentiate this, so what we will get here is, that is ktv, that is ktv minus here tc kv. So here what is tc? So tc is centrifugal tension, and its value is for the tension value is mv square. So as we know that centrifugal force is mv square by r, so for centrifugal tension is mv square. So here I can write, so here we are trying to differentiate with velocity here. So d by dv is equal to here ktv minus mv square kv. So here it will be velocity cube, and then we can try differentiation. So now let's try differentiation. So differentiation of v will be equal to 1. So here the ktv differentiation will be kt minus here m is constant, k is constant, and v square and v cube. So differentiation of v cube will be 3 outside and v square. So there is 3 here comes, and 3 minus 1 will be 2. So here the differentiation we are equating this differentiation is equal to 0 here. So we are left with, if I bring this term negative term on the right side, so we are left with m 3 mk v square is equal to kt. So 3 mk v square is equal to kt. So if let's see what the terms are getting cancelled. So here k will get cancelled. So here we are left with t is equal to 3 mv square. Now what is mv square? So mv square is nothing but centrifugal tension. So we can write here t is equal to 3 times tc, or we can write tc is equal to t by 3. So for maximum power transmission, the centrifugal tension in the belt is equal to one third of the maximum allowable belt tension, and belt should be on the point of the slipping. Also, as we know that total tension T is equal to T1 plus TC. So therefore if I have to find T1 here, so T1 is equal to T minus TC. So it is T minus T by 3. So it will be equal to uh, 2 2t by 3. So the initial, there is tension T1 will be equal to 2t by 3. So also T is equal to T, also we know that T is equal to 3tc. So we know that T is equal to 3tc, so which is equal to 3 mv square, that is 3 mv square. So v max, if I were to find maximum velocity, so it will be equal to t divided by 3m. So this few formulas which we have found which we will use in examples. So, tension on the tight side is 66% of the total tension, and on the slack side is 33%. So as you can see, there is 2t by 3, that is 2 3, that is 66%. So this is the tension on the tight side. This is the maximum velocity that is possible, that is total tension divided by 3 divided by 3m under root. So this is the total power developed. So in the next lecture we will see few other topics related to the belt drive and also chain drive. So thank you very much.